So before we start, there is a question on the chat. How does one determine the environmental flow? This is a very good question, and it is a question that may be asked at the exam, actually. So I think it is indeed a good intuition that what you had. So how does one determine the environmental flow? First of all, there is an order of magnitude that I would like to give you an idea. And there was some years ago in Switzerland a rule which was imposed by the laws in force. And the rule was that the environmental flow should be determined by assessing the flow with a duration of 355 days, 355. So to give you an order of magnitude, and it is more or less, let's say, lower than, of course, the average, much lower than the average, and it can be estimated as also as a portion of the average, and I would say that one may say that it's about 2-3% of the average flow. Just 1 second. Okay, and so this is just to give you an order of magnitude. So remember the Switzerland old rule, flow with a duration of 355 days, which means, by the way, that if a river is intermittent, then the environmental flow is 0. This is the implication of this rule of thumb. Now, actually, how should you determine the environmental flow? In almost all countries in Europe, you have rules, laws in force that give you suggestions and typically give you empirical relationships for estimating the environmental flow. For instance, in Italy, and why I'm saying in almost all countries of Europe, because there is a European deliberation that goes back to the year 2000, so it's already more than 20 years old, which imposes to the member states to issue regulations, to issue laws, to impose the respect and the release of the environmental flow. And these regulations are also in charge of giving technical guidelines for its estimation. So depending on how the European deliberation is adopted in each country, you may find different administrative settings. To give you an example, in Italy, the Italian government delegated to the regions this task. So you have to look at the regional regulations, the regional laws in Italy in order to find the guidelines, the technical guidelines for estimating environmental flow. And for instance, I give you an indication for our region. If you go to, let me open a new web page. If you go to Google and you search for Emilia-Romagna, which is the region where we are in Bologna, and you write Piano Tutela Acque. In Italian, you see that in Google it's already predefined the search. And in Italian, the water management plan, it's called Piano Tutela Acque. Now, if I go here, you get to the web page dedicated to the regional plan for water management. And here you see the links where here you can find the plan and the documents. And in particular, if you go down, here it is. And here you see the rules. If you click on norme, which in Italian means rules, you get to just, we need to be patient a little bit. You finally get to a PDF document. And of course, let's see, I think this is the comprehensive document, le norme. Let's see. And here I open the document and you see the rules, the norms of the water management plan. And if we look here in the table of contents, I think we can find here in the technical guidelines for the environmental flow, and let me see where it is. And I need to let me see where it is. And okay, I think it is here. It's the norm number. It's the Article 52. It's called the Flusso Minimo Vitale, as I mentioned to you last time. And let's go to page 33 then, and let's see what's there. I need to browse forward just 1 second to Article 52, and here is let's see, here it is, the Flusso Minimo Vitale. And here I think let's jump to the technical guidelines, and here it is. DMV components, it means components of the environmental flow, because the Emilia-Romagna region gives 3 components, and then here you see the relationships. Okay, this is one, this is another one. We don't go into the details, but if you look at these norms, you find all the relationship technical guidelines to compute it. Okay, and this is an example for the Emilia-Romagna region. If you're interested in another region of Italy, you just have to change in your Google browsing, you just have to change the name of the region. And for any other European country, you should look at something in Google, like, for instance, Romania and environmental flow, and then you get indications. Of course, you have to be a little bit skilled in browsing the web. It may happen that in some countries, the European deliberation has not been adopted yet. This is something that may happen. For instance, even in Italy, there were some regions that were in delay in issuing the norms. So it depends on the particular situation. Of course, if you refer to a region where you struggle in identifying what are the reference laws, you should try to get more detailed information. And at the end of the story, if you conclude that you don't have any technical guideline available, you have to adopt international standards, like, for instance, the Swiss rule of thumb, or other international guidelines that may be sound for the region of interest. So this is more or less the situation. And of course, like in any design activity, you have to adapt, you have to try to get the preliminary information that you need, and you have to adapt to the situation that you are experiencing. Because when we work in an international context, even in the national context, you may find some diversity or some inconsistencies. And in the international context, of course, you have to be ready and flexible to adapt to different situations that you may experience. I hope that the reply was exhaustive. Okay, now, if you don't have any more questions, again, I go back to deductive methods. So inductive methods, as I said, are based on data analysis. Deductive methods start from the theory, and then in general, they start from the knowledge, from the available knowledge. They try to establish, to build a model. In the deductive methods, you build a model that profits from your knowledge, profits from some input data, and delivers an estimate which may be independent of observed data, an estimate of the design variable you are interested in. So in our case, the design variable is water resources availability, and therefore the aim is to build a model that is able, starting from input data and starting from our available theory, this model is able to deliver to you an estimate of design variable, again, you are interested in. And it's different with respect to the inductive approach, because, as I said, you start from the top of your knowledge, and you go down to try to reproduce the process. in mathematical terms, reproduce the natural process you are interested in to generate the output from this process, which is your design variable. In our case, we start from our knowledge of the hydrological cycle because we want to reproduce river flows or groundwater flows. Okay, so our assessment of water resources availability means an estimate of river flows or groundwater flows. So inductive methods derive this estimate by analyzing observations. Deductive methods start from our knowledge to reproduce the process, which is in this case a part of the hydrological cycle, to reproduce the process through a mathematical relationship, and then simulate through this mathematical relationship precisely the river flow or the groundwater flow. Let me check. Yeah, okay, no more questions. So this is what we are talking about. So when we talk about deductive methods, usually we talk about models. And we talk about mathematical models. Of course, it is something that we expect to be a little bit more mathematical with respect to analysis of the observations. On the other hand, you know, it's also the analysis of observations involves some math because we talk about probability, statistics, etc. And therefore, we are already used to use maths for making this assessment of water resources availability. But this is a different math because in this case, we try to build a model that reproduces the process. Now, let's start from surface water availability. And therefore, the kind of model that we want to build is what is called in the literature a rainfall runoff model. You see that there is a Wikipedia link here. If we click on here, there is a definition of what is a rainfall runoff model. Some of the part of this description is copied in my web page. Okay, so why do we choose this rainfall runoff model? So if we want to reproduce the river flow, which is the result of runoff. Okay, runoff is the part of rainfall that does not infiltrate and flows over the Earth's surface. So you understand that runoff is what forms the river flow. So why do we build a rainfall runoff model? Because if we want to reproduce the river flow, we want to reproduce the runoff. So again, the part of rainfall that does not infiltrate. And what is producing the runoff? Rainfall is producing it, or let's say in a more general context, precipitation. But in technical terms, they are called rainfall runoff models. So again, it's precipitation that generates it. And therefore, it's called rainfall runoff model because we start from precipitation to reproduce river flow. And therefore, the chain is precipitation, rainfall, runoff, river flow. So we need a model that transforms rainfall into runoff. Now, keep in mind that precipitation and rainfall are often used as synonyms. What's the difference? Precipitation includes, besides rainfall, also snowfall. And other form of precipitation like condensation of fog, for instance. So with the term precipitation, we mean something larger than rainfall, but in temperate climate, usually rainfall is synonym of precipitation. Okay, so don't worry about using precipitation rather than rainfall. We use rainfall runoff to term these models, but don't worry, one term or the other is equivalent. Just beware of the difference. Okay, so what is precipitation? What is rainfall? Okay, rainfall is precipitation in liquid form. Okay, so why do we use this model to solve a lack of data? Because usually, as we said, when we have observations available, we prefer to use directly observations to infer water resources availability. So we don't want to use a mathematical model to reproduce observations when we already have observations. We use a mathematical model when we don't have observations or when observations are limited. And why? What is the practical reason why a model can resolve lack of data? The reason is very simple, because measuring river flow is complicated. We have only sparse measurements. It's very infrequent, the situation where you have observations of river flow in the site of interest. For rainfall, the situation is different. It's much easier to measure rainfall. You just put a pot outside your house, your home, and every day you look at the water content into the pot. And in measuring rainfall is very easy. So the result is that we have plenty of data about rainfall, while we don't have much data about river flow. So the rainfall data availability is much higher than river flow data availability. And for this reason, we are interested in, we conceived the idea of using rainfall data to derive river flow data. So this is why we use rainfall runoff models. Now let me back to my web page. Let me go back to it. Rainfall runoff modeling. So as I said, we need to build a mathematical model to reproduce the river flows. We need a mathematical model relating rainfall to river flow. It's quite naive as an idea. It's clear that this is a good solution. Of course, while the idea may look even naive, building this set of mathematical relationship is not easy. And in particular, what is the natural process that we have to emulate with a mathematical model? It's the water cycle, is what you see here. So we don't spend many words on the water cycle. This is a classic figure taken by the United States Geological Survey. It's also used in the Wikipedia page that I showed you before. And this is something, as I said, that we don't treat into detail, because we know about the water cycle since we attended the primary school. It's a well-known concept, and we know that the water cycle is the basic for life over the earth. It's something extremely important. The water cycle governs the climate, governs nature, and it is the engine powering the water cycle is energy from sun. One thing that I think it's important that you put in your mind is the fact that we still know very little about the water cycle. We know the big picture, and the big picture is what you see on the screen now. But if we go to look at the details, then it turns out that there are many unknowns. And the unknowns are diverse. I mean, there is a part of the unknowns that is just related to limited knowledge of the system. So think of a river, for instance. We don't know anything about a river. Think of the geometry of the river. We may ask a surveyor to take some surveys of the cross-river sections, but still, there will be a few cross-river sections that you may take for getting a description of the geometry. This is by far not equivalent to a full knowledge. So for instance, let's think at the downstream reach of the Po River. It's about 200 kilometers long. It is described with something like 100 cross-river sections, which means that you have, on average, a river cross-section every couple of kilometers. It's nothing. I mean, in terms of gaining a full knowledge of the geometry, it's nothing. So there is a partial knowledge of the system. There are unknowns in the system, and these unknowns become much relevant if you think at the groundwater flow. If you look at this figure here on the bottom left, there is the groundwater discharge and groundwater storage. We don't know anything about the underground, or let me say, we just know a little, a very little of it. So this is a reason of limited knowledge, but there is also another reason of limited knowledge, which is our lack of understanding of some phenomena. How does it take place, the groundwater storage? And what is the interaction between groundwater discharge and groundwater storage? Or again, evaporation, which is something that we think it is well known. Actually, we don't know how it works in nature, in reality. And I give you an example. There was, and there still is, a global belief that with global warming, evaporation is increasing. Of course, you increase the temperature and then you increase evaporation. Actually, it's not like that, because it turns out that with global warming, the wind speed decreases, and the wind speed is a strong driver of evaporation. If you increase the wind speed, evaporation for the same temperature increases a lot. So it turns out that with global warming, you have more potential evaporation, but on the other hand, you have less wind speed, and therefore it turns out that at the global level, under global warming, we have less evaporation. So this is an example to show to you that our knowledge of these natural processes, our knowledge of the water cycle is still limited. And of course, this is a reason of uncertainty. When we go to the technical design, when we go into the domain of our profession, we have to make a design on the basis of something that we still don't know in detail. And of course, we try to resolve the situation, to resolve the unknowns by looking at data. But in this case, we start from the preliminary assumption that we don't have enough data. So we have to build a mathematical model of something that is unknown. And then we need to resolve this gap. How to resolve this challenge? Of course, the scientific literature devised a lot of possible solutions. And therefore, with this lecture, I want to give you just a brief glance, a brief overview of these optimal solutions, of these solutions, potential solutions. And then this is the reason why we talk about rainfall runoff modeling, which I think it is really a fascinating subject. It's fascinating because you know, it's something that is still a discovery for us, for humans. It's something that it's continuously evolving. And therefore, I think it's stimulating. We just don't have to repeat something that has been done for hundreds of years. It is something that it's really new, really evolving, something that requires a continuous update of our knowledge, of our knowledge of the scientific literature. So again, it's exciting. Now, let me go to the PowerPoint presentation, but before doing that, I just wanted to make sure that I refer to, just one second, here I am. Okay, to the web page, to the large web page, okay. Okay, so the PowerPoint presentation may be useful. F5, here it is. And now, again, let's focus on surface water. And we are already here at rainfall runoff modeling. So rainfall runoff models don't describe the whole water cycle. They describe just a part. And precisely, they aim to describe the processes that governs the transformation of rainfall into runoff. So what is the reason why we focus only on a small part of the system? To reduce uncertainty, of course, to make models simpler. You understand that a full descriptive model of the whole water cycle, it's something that it's more complicated with respect to a small portion of it. And usually we refer to a fixed location in space. We don't want to model the whole Earth system. We don't want to model the rainfall runoff transformation over the whole globe. This is something that is possible. People are trying it. But in order to simplify the problem, we focus on the place where we are working on. We are engineers. We need to find the most practical solution. And keep in mind that most practical for us doesn't only mean the easiest one. We are not looking for easiness. We are looking for limited uncertainty. This is what the engineer is looking for, keep in mind. So we are not concerned about complexity. If a solution is a good solution, then we don't care about complexity. We have a good mathematical background, we are engineers. What we care of is our responsibility. So our duty, what is our duty? Our duty is to deliver a good design. And good design means that we have to reduce uncertainty, because actually this is the primary criteria for evaluating if a design is good or not. You have to look at uncertainty. So if the engineer is able to minimize uncertainty, then they are very good engineers. So this is our target. So again, we are not looking for easiness. We are looking for the approach that reduces uncertainty at the minimum. And this is why sometimes we use very simple relationship, because there is a direct association between complexity and level of uncertainty, with exceptions. But the rule of thumb is that the more the complexity, the more the uncertainty. And I will explain to you why. It's very easy to understand this. But keep in mind this rule of thumb. So the more the complexity, the more the uncertainty. And this is why we sometimes look for easy models, not because we are concerned about complexity. We are only concerned by exploding uncertainty, inflating uncertainty. Okay, so look at this last bullet point in this slide. Depending on their complexity, models can also simulate the dynamics of river quality, ecosystems, and other dynamical systems related to water, like ecology and society, something like that. But again, in doing this, you increase the complexity. And this is why sometimes we prefer more focused models. So we forget about links with ecology, not because we are not interested in ecology, but because we don't want to increase the complexity. And keep in mind that today there is a continuous search for complexity in research, because we understand the interaction between water resources, climate, ecology, humans, society, and we want to describe all of it. Of course, we are interested in describing climate because we are concerned by climate change. So there is the temptation to include climate models into hydrological models, or the other way around, to include hydrological models in climate models. And this is something for which we have a continuous push, which is also favored by the modern computing technologies, computing resources. We have more computers, we have more computational capabilities, and therefore we are tempted by complexity. But we are engineers, and we have to be very careful about increasing complexity, because again, our primary concern is uncertainty. Look, I am insisting because this is not clear. If you read the literature, if you read books, especially modern books, this is not clear. In old books, this was implicit. In old books of engineering, it was implicitly accepted that it was given for known that the primary target is to reduce uncertainty for an engineer. In modern supporting documents for education, including books, this is not clear. So this is why I am insisting. Okay, now, how do we build a model? And let me go back to the web page because I think it is more, there is this figure from which I want to take inspiration. So we want to reproduce the part of the hydrological cycle that is related to precipitation and runoff. And how do we build this model? So there is, again, a principle that should guide you. And the principle is that you should refer to the laws governing the processes that you want to describe. So what is your purpose? Let's keep it in mind, is to build a mathematical model reproducing a natural phenomena. Mathematical model means equations. What kind of equations should I use? Again, you should look at the laws governing the processes you want to describe. What is the process that you want to describe? It's movement of fluid, movement of water. What is the science governing the movement of bodies? It's physics. Okay, so you should look at the laws of physics, and in particular the fundamental laws of physics, which are also called the Newton's laws, but let's call them the fundamental laws of physics. These are the laws that you have to refer to, because again, you want to describe the movement of a fluid. And what is in particular the branch of physics that describes the movement of flow? It's fluid mechanics. Okay, so we got to the idea of looking at fluid mechanics, and then fluid mechanics, we know from our background that the fundamental law of physics apply to it, and in particular in fluid mechanics we can apply some conservation laws like mass conservation, energy conservation, momentum conservation. I think you are familiar with mass and energy. You know what mass and energy are. And in particular, now we are talking about water. So we are talking about mass of water, energy of water. Maybe that you are less familiar with momentum. Momentum is related to energy. Let's not go into the details because we don't need to go into the details of fluid mechanics. What I want you to get is the train of thoughts that brings us from the practical need to describe the rainfall runoff transformation to the deduction that we have to apply conservation laws of physics, and in particular conservation of mass and conservation of energy. Then if we go deep into fluid mechanics, there might be other conservation laws that we call into play, conservation of momentum, and maybe other conservation laws like conservation of heat. But we don't need this detailed now. We don't need this level of detail now. So let's focus on the connection, the train of thoughts between the practical need and conservation of mass and conservation of energy. So in rainfall runoff modeling, we have to apply conservation of mass and conservation of energy, explicitly or implicitly. We will see the difference, okay? what is the domain with respect to which we apply these conservation laws? When you apply a conservation law, you have to define the domain, which may be, for instance, a room. If I want to apply the conservation of the mass of air, I need to identify a volume, maybe a room. If you want to apply the conservation of mass of water, you have to identify in the same way a volume, like, for instance, a glass or a bottle. In a bottle, you can apply conservation of mass because you may feed the bottle by pouring water into it and you may drink part of it. So it's very easy to apply mass conservation for the bottle, but you identified a volume with which you apply the conservation. This is called the control volume. What is our control volume? First of all, let's say that our control volume is fixed in space, and usually it corresponds with the catchment. Okay, what is a catchment? Let me see in the web pages if there is a definition of the catchment. I hope yes, and let me just look for catchment here. Okay, let me see. Okay, so this is something that I have to introduce here because it seems that it's not defined. Okay, very good. So I will introduce it in the web pages, but before introducing it, let me give you the definition, okay? And in order to look at the definition, let me open another web page, Google, and let's look at catchment definition. Let's take this, okay? I would say that, let's see, catchment. I would prefer a definition which is not taken from a dictionary, but we need a definition of a scientific definition of it. And let's see, catchment hydrology, Wikipedia, maybe. let me see. Otherwise, we can give the definition in. I can give the definition directly. I was looking for a reference. Let me see. It seems to me that it's impossible that there is no definition. Let me see. Drainage basin. Yeah. So it's the catchment has many synonyms. So you can say catchment, you can say basin, you can say watershed, you can say drainage basin. So these are the synonyms. I repeat them: catchment, drainage basin, or simply basin, or watershed. And this is a definition that we may adopt. A drainage basin is any area of land where precipitation collects and drains off into a common outlet. And I would say that we can adopt this definition, or let me say that I would prefer to define it in a more rigorous way. So let me give you a more rigorous definition that I will put into my web pages. So I would say that a catchment is defined as a portion of land such that precipitation falling over it is drains to a given river cross section. Okay, this is the definition that I would adopt, and I would correct it in this way. And again, I will include the definition in the web pages. You will find it during this week. So I would correct it in this way: a catchment is a portion of land such as precipitation falling into it, and only that precipitation drains into a given river cross section. So with respect to the previous formulation, I added only that precipitation. And here you have an illustration of a drainage basin, which is fine. I mean, it gives you an idea. So if I open this, you see that there is a portion of land which is limited by a dashed red line, which is called the catchment divide, because it divides a catchment from a neighboring catchment. And here you have a portion of land such that all and only the precipitation falling over it drains to the outlet, and the outlet is the given cross river section. Okay, so this is our control volume. You may say, but this is not a volume, it's a surface. Actually, if you include the underground, because precipitation may drain not only through the surface, it may drain through the underground. So if you include the underground domain of the flow to the given cross river section, then you get a volume. So basically our control volume is the catchment intended as catchment area plus underground domain of the catchment. Is this clear? So this is our, again, control volume where we apply conservation of mass and conservation of energy. Any question? Let me look at the chat. I keep the chat on the second screen so I can look at it without changing your view. Okay, now it looks like this is a complicated stuff. So I want to give you an example to show you that this is not complicated at all. I mean, try to make a difference between understanding and application. Understanding may be complicated, application may be simple, or the other way around. In some cases, you will find understanding is very easy, application is troublesome. In this case, I mean, behind our approach, there is an understanding that you have to gain of the water cycle and your target in a more detailed way with respect to what you're used to learn in the past. Okay, so you have to understand the water cycle with its unknown and its interested domain, control volume, conservation of mass, conservation of energy, etc. So try to get a clear perception of how these concepts that I introduced today combine together. And this is the most complicated part of it. So try to understand that what you see of the water cycle is indeed governed by physics, and we can describe it through conservation of mass and conservation of energy applied to a control volume. Okay, I'm just looking at the chat. Okay, very good. Now, let's make a simple example to show you that, indeed it may be simple, the solution. And let me make the example of the first rainfall runoff model that was ever proposed, which is called the rational formula. The rational formula, as we will see, is something that is not very useful in water resources management. It's very useful in designing infrastructures for flood mitigation and flood protection. The rational formula was proposed about 200 years ago by two scientists, an American scientist named Kuchling, I don't know the correct pronunciation, who, by the way, and we must say, elaborated concepts that were previously proposed by an Irish engineer, Mulvaney, in 1851. And an engineer, it's not coincidence, okay? It's not a coincidence, because it was an engineer, the first, who had this necessity to describe the rainfall runoff transformation. And the rational formula, let me look at the PowerPoint because it's larger, I think. Just 1 second, I get to the presentation mode. Here we are. The rational formula reads in a very simple way. It describes the river flow, and let's describe it with the symbol Q, and let's forget about dependence of time. It's only Q, without Q and between parentheses T, okay? So let's forget about the dependence on time. Q refers to a given cross river section, and Q is expressed as the product of 3 factors. And CIA, what are these factors? First of all, it's called very often CIA formula by establishing an analogy with the American CIA, because it's easier to remember in this case. And what are C, I, and A? C is a reduction factor, which is called the runoff coefficient. And let's discuss about it later on. I is rainfall intensity, and A is the catchment area. So let me take the graphic blackboard, because I want to make you a sketch, because this formula, it's very simple, and yet it's understanding the basis of this idea allows you to effectively understand the concept behind the rainfall runoff modeling. Okay, just 1 second, I get here the graphic blackboard. Now, first of all, we have a catchment, and let me depict a catchment over here. And the catchment is like this, and you have a river here. Sorry. Okay, you have a river over here, like the figure that we saw on Wikipedia. Okay, and this is like a map of the catchment, and you have over this catchment some rainfall falling into it with an intensity I. What is rainfall intensity? Rainfall intensity is given by I. Rainfall intensity is given by the ratio between rainfall depth, which we may call D, divided by the time during which this rainfall depth occurred. So you have some rainfall, and like, for instance, think of a pot that you put outside your home, and it starts raining. So you have some rainfall falling into it. Okay, so you have some rainfall. And after a while, you go out, for instance, after a couple of hours, after 2 hours, you go out and measure a rainfall depth D, okay? Then, in order to compute your intensity, you precisely look at this relationship here. And rainfall intensity I is given by the ratio, as I said, between rainfall depth and the time in which rainfall occurred. Remember, when you talk about a rainfall event, you have to define the location where rainfall was observed and you have to define the duration. This is an extremely important behavior of a rainfall event. You cannot talk about rainfall if you don't specify the duration of the event. For instance, sometimes we talk about annual rainfall. The duration is clear, it's the year. Or we talk about daily rainfall. Again, the duration is clear, it's 1 day. Or we talk hourly rainfall. Again, duration clear. If we just say rainfall in Italy, no meaning. You'd have to specify the duration. And then once you know the duration, then by dividing the rainfall depth by the duration, you get the intensity, okay? What is the dimension of the intensity? It's length divided by time. Very good. Now, what is the idea of the rational formula? And let me change the color. The idea of the rational formula is that you have some rainfall I falling over the catchment, and then I want to compute the river flow Q at the outlet, and Q is here. Let me write it here, okay? So the idea is very simple, is if I multiply rainfall intensity times the catchment area, and this is the catchment area A, what do I obtain? From a dimensional point of view, what is the dimension of E times A? The dimension is precisely length divided by time times length square. And then this is equivalent to L cube divided by time, which is a volume divided by time. It is precisely a river flow. So the idea is that if I want to get the river flow from a catchment, I just multiply the rainfall intensity by the catchment area. And given that I have some water losses, because there is some evaporation, there is some deep percolation, water that goes into the ground and we will not see anywhere anymore, then I add here a reduction coefficient C. And then in order to make it more easier to remember, then I rewrite it as CIA. This is the rational formula. You see that the idea is very simple, but there are some open questions, which it would be nice to see if you can get them. And what are the open questions? And I just want to give you a brief overview of them. So the open questions are, first of all, let me change the color. How do we estimate the rainfall intensity? Because I just said that rainfall refers always to a duration. So what is the duration of the event that I have to put there? Should I put there annual rainfall, daily rainfall, hourly rainfall? And in any case, how to estimate it? Okay, first question. Second question, C, the reduction factor. Of course, I said it's a reduction factor, so C, it will be in the range 0, 1. But what is the value that I have to put there? Because you see that it's a big difference. I mean, this reduction factor has the potential of annihilating the river flow or bringing it to a max value. So if I change the reduction factor 20%, I am changing river flow 20%, which is a lot. So this is an open question. Another open question, which is not so relevant actually, catchment area, how can I estimate it? So let's discuss these questions now by going back to the PowerPoint. And I make a break in let's say 20 minutes, 25 minutes from now. So, first of all, let's note that the rational formula is dimensionally homogeneous, and therefore you should make sure that you use coherent units. So if you measure the catchment area, for instance, in square meters, which is unusual because usually we measure the catchment area in square kilometers. But let's suppose that, let's say that we need to be homogeneous, and therefore in terms of units, and therefore we have to measure the catchment area, for instance, in meters, in square meters, and then also rainfall intensity should be measured in like meters per second. And then the result that you obtain is river flow in cubic meters per second. Okay, so let's pay attention to the units first. And then let's say that let's focus on the open questions that I mentioned before. For the duration of the rainfall event, so this is something that is indeed relevant. And I want to give you a rule of thumb by saying that this rule of thumb can be proved with physical reasoning, but we don't prove it because we don't get too much into hydrology. We have to stay into water resources management. And if we deviate too much, then we don't have time to discuss the basics of water resources management. I don't want that. So let's just give you the rule of thumb without any proof. And so the rule of thumb says that you should select rainfall for a duration of the event which is equal to the time of concentration of the catchment. Okay, what is the time of concentration? You see the definition here in the second bullet point. The time of concentration is defined to be the time required for a fluid particle to travel from the most hydraulically distant part of a watershed to the outlet. So it's the max travel time of a drop of water. Okay. Look, this is something that is defined in this way. Implicitly, we say that we focus on surface water paths, not groundwater paths. Okay, so it's the time required for a fluid particle to travel over the land. Usually it's omitted. Over the land in the definition of time of concentration, it's omitted, but implicitly it's taken as a fluid path that is over the land. Okay. Now, let's focus again on the time of concentration. How can we measure it? There is no way to measure it. It's estimated through empirical formulas. In Italy, there are several formulas proposed by the literature. In Italy, we use a formula that is called Giandotti's formula, which was proposed about 70 years ago, 80, I would say, by an Italian engineer called Giandotti, whose name was Giandotti. It's very used in Italy. In the literature, you may find other formulations. I'm not interested in these empirical formulations. These are empirical relationships. I'm not interested in them, and you shouldn't learn them. You should just learn the definition of catchment and time of concentration. Okay, the definition of catchment, again, I will put it into the web page. Now, this is then the problem of estimating rainfall intensity, which is now solved. Okay, now let's focus on the problem of estimating the reduction factor. I'm not sure whether it's discussed here or in the next slide. It's not discussed here, but it's discussed in the web pages. So let me go back to the web page, which is here. And let me see where. First of all, sorry, because I forgot. Before discussing the reduction factor, I left a question open. I said that rainfall is to be estimated, rainfall intensity, for a duration which is equivalent to the time of concentration. But what is the method that we apply, the technical method that we apply to estimate a rainfall? First, we don't go into the details. This is hydrology. There is a relationship which is called the depth duration frequency curve. If you click on the link, you get a scientific paper defining, it's by me, sorry for that, defining what is a depth duration frequency curve or equation. Let's forget about it. I just want to inform you that it's a inductive relationship that, basing on rainfall data, gives to you an estimate of the rainfall depth for a given duration and for a given frequency. What does it mean, frequency? It means a return period. It means that you have to estimate the rainfall that corresponds to a given probability of occurrence, and which is the return period. I guess that you already know what return period means, but in case you don't, it's easy to find information, and again, we are not focusing on it. I just want to tell you the basics, and the basics is that when you estimate rainfall, you have to refer to a location, to a duration, and to the frequency of that rainfall, which means that if you refer to a rainfall event that occurs very frequently, it's a different story if with respect to referring to a rainfall event that may occur once every 10 years on average. Okay, and again, the reduction factor. The reduction factor, it's something that it is discussed here. A relevant challenge for the application of the rational formula is the estimation of the runoff coefficient, namely the reduction factor, which typically varies between 0.4 and 0.6 in natural catchments. So these are the most likely values. Remember that when you want to be safe, you may increase it. So the max river flow, if you are interested in the max, is given by a reduction factor of 1. The mean river flow, if you are interested in the low flows, is given by a reduction factor which is 0. And between these two extremes, you can play your safety level. Okay. And then there is the catchment area. The catchment area is easy. It's something that can be estimated with a map. You identify the cross river section you're interested in, and then you follow the catchment divide on the map. Okay, the catchment divide is what is the definition? It's the divide of water. So any catchment has a neighboring catchment, and there is a ridge dictating, dividing the water that goes to your catchment and the other catchment. So you can just follow the divide over a map, and then you get the catchment area. Okay. And then once you have defined the reduction factor, the rainfall intensity, and the catchment area, you can easily apply the rational formula. There are some assumptions here that are worth discussing. So, and the assumptions are listed here. This is a comprehensive list of the assumptions of the rational formula. And given that the rational formula, and it's discussed here, given that the rational formula is frequently used when estimating the peak flow and rather than the low flows, and I explain you why, usually these are the technical applications where the rational formula is most frequently used. And here, look at the last sentence. Being focused on the estimation of peak river flow, the rational formula is generally not very useful for assessing water resources availability. It's very useful as an example of a rainfall runoff model. Now, why is the rational formula used for the peak flow rather than the low flows? Because it essentially describes the surface runoff and doesn't describe groundwater runoff. The rational formula, by expressing river flow as a fraction of rainfall, basically it doesn't take into account that part of the rainfall infiltrates and may stay in the underground for months before getting to the closure, to the outlet of the catchment. But actually, it is this part of low response that is important for modeling low flows. We are interested in assessing water resources availability with particular reference to the dry seasons. And therefore, it is this groundwater flow that is relevant to us. The rational formula doesn't describe it. The rational formula doesn't describe storage. It just gives the river flow as a fraction of rainfall. So it's good for floods, for peak flows, because peak flows are indeed generated by the surface runoff, by the rapid runoff. The contribution of groundwater flows to peak flows generally is very low. Now, low flows is different. So this is why the rational formula is not much used. So given this premise, let's look at the assumptions. The computed discharge is the max that can occur for the selected rainfall intensity from that basin, and that discharge occurs at the time of concentration and beyond. This is the assumption that allows us to use the time of concentration as an estimate for the critical rainfall duration, for selecting the rainfall duration. Second assumption, this is very important. The peak river flow, or the river flow, let's say, it's directly proportional to rainfall. There is a direct proportion between rainfall and river flow, which means that the model is linear. The frequency of the peak discharge is the same as the frequency of rainfall. You know, given that the relationship is linear, there is a coincidence between the frequency. Remember, we talked about the frequency of rainfall. Then the river flow occurs with the same frequency. The drainage basin is considered linear. This is a consequence of assumption 2. Here there is a spelling error. Sorry, I will need to correct it. The coefficient of runoff C is the same for storms of various frequencies, is a constant of the drainage basin. And it's the same for all storms, regardless of antecedent moisture condition, which is not very reliable because, you know, when it rains over the wet soil is a different situation with respect to when it rains to dry soil. There is a different infiltration, but the rational formula doesn't describe groundwater flow. Another assumption, rainfalls remain constant over the entire watershed during the time of the event during the time of concentration. So constant rainfall over the catchment, constant rainfall in time. And again, rainfall occurs nearly uniformly from all parts of the watershed, so it remains constant over the watershed. These are the assumptions, and I think it is interesting to look at this assumption because they allow you to comprehend, to understand how the process takes place. So you have to be aware that over a catchment, rainfall is not constant. It's not constant in time, is not constant in space. We are trying to describe with a mathematical relationship a phenomena which is actually very complicated. And okay, that's it. But I think this is a very good example. Let's go back here to the rational formula. It's a very good example because it is very simple. And through simplifying assumptions, we reduce a complicated problem to a simple relationship. And what is the reason why we use it? Because actually it's widely used. We use it because being it simple, uncertainty is something that it's relatively limited and very easily manageable. So uncertainty here is mainly related to C, to the runoff coefficient, which we call the reduction factor. And it's very manageable. If I want to reduce the uncertainty, I increase or decrease C accordingly. So, I mean, I think it is a very interesting example of something whose uncertainty is completely, if not reduced, under control. But what I said is that indeed it's not very useful for us because it refers to peak flows, not to low flows. So how to build a model that accounts for low flows, and then we need to account for infiltration, for groundwater dynamics. So let's move a step forward by introducing a second model which allows to move a step forward in describing the low flows. And this step forward would be the linear reservoir, or I can also go on the PowerPoint and look at the linear reservoir here. Before I move forward, any question? You know, today the lecture was a bit, it's a bit technical. So I am surprised that you don't have any question for me so far. There is one thing that I wanted to ask you, and let me make a poll for it. An anonymous pool, just 1 second.
Prof, there's a colleague waiting to be allowed into the class.
Yeah, I think I allowed him to get in. Just 1 second, because I don't understand for what reason I get from this person more than once the request to be admitted. So I admitted him at the beginning. Before I started with a pool, so let me make the pool and then I will check if I need to remake the admission. Just 1 second. I am making an anonymous pool, which I am now putting into the chat. So please vote, and once that you see it, and let me see now if I can admit the person. Let me do like this. Now there is no one waiting to be admitted. And now let me see the pool, if you can see it. No. So what is the reason why? Just 1 second. I think I was too hurried, so let me do it again. Okay, it's here. Just 1 second. I just have to send it. Okay, I made a mistake. Just 1 second. 1 second, I put the question in another chat. Okay. Let me remake the question now. Okay, very good. Here we are. Perfect. Still, the system is giving to me some problems. Just 1 second. Okay. Okay, here we are. Sustainable design of water resource system. Let's try in this way. Okay. Okay. Okay, I think you should see now the form. Let me see. Yeah, can you please vote? It's anonymous. Okay, very good. Only 3 votes so far. Okay. 5 votes. Okay, so I believe that I think most of you know what is the return period, but there are still some students I don't understand why. Probably it's no vote probably. Okay, so I think I will better include a definition in the web pages. Okay, so I believe that we can make our break now for 15 minutes. So see you at 11. Thank you very much. Okay, here I am. Just 1 second. I need to go to my graphic keyboard. Sorry, graphic blackboard. And let me open a new one. Okay, very good. Perfect. And now let me first ask you if you have any question. Let me see on the chat. And okay. No other questions. And now let me share the screen. Okay, good. Now, I think you should see my graphic blackboard. I don't have my phone to check, so please, if you don't see the graphic blackboard, just let me know. And I want to introduce the linear reservoir model. So we are talking about, sorry, because it's too big. Okay, here we are. So, okay, linear reservoir. So, what is the linear reservoir? The linear reservoir is a rainfall runoff model that aims also to reproduce the storage operated by the basin. Let me check if the recording is still going. Yes, and keep in mind that in the video there will be the break, which is empty, so you will get the 15 minutes with no lectures and just skip it, okay? So the linear reservoir, as I said, aims to reproduce the storage also operated by the catchment. And it is based on a very simple conceptual scheme. So it is based on representing the catchment as a tank. Oops, sorry. The catchment has a tank, as I said. And here is the tank. So this is our catchment. It's a tank with a bottom discharge. And the assumption is that we get rainfall falling into the tank. And let me check just 1 minute. I want to make sure that I use the same symbols. Yes. So the rainfall is called PT. So here I am introducing the dependence on time, okay? And then rainfall falls into this tank, and there is an accumulation of water into the tank. And the volume of water is indicated, the volume of water into the tank is indicated with the symbol W. And from the bottom discharge, we have an outflow QT. So you see a first difference with respect to the rational formula, which is the dependence on time, which means that we are not describing a constant flow. The rational formula describes a flow that is supposed to be constant. So after a rainfall, you get a Q that is constant, okay? Here, you get a river flow that is varying in time, and also rainfall is allowed to vary in time. And a second difference that you see is that there is a description of the storage, okay? So, first of all, let's clarify what is, how is rainfall described. You see that there is indeed a different symbol to describe rainfall. I'm not using I anymore, I'm using P, and the P is rainfall intensity times the area of the catchment. So is a volume of rainfall over the catchment per unit time. Again, it's a rainfall intensity per multiplied by the area of the catchment. W is a volume of water that is stored by the catchment. So, as you see, this is a quite understandable and motivated representation. I have some rainfall falling over a catchment. I admit that there is some water stored by the catchment, and then there is an outflow QT. Let's say that the rainfall, besides being obtained by multiplying rainfall intensity by the catchment area, is also assumed to be a net rainfall, which means that any losses derived from evaporation or any other kind of losses, it's already subtracted. So let me write PT is net rainfall volume per unit time. Good. Now, I can easily apply a mass balance equation to this scheme, to this tank. And the mass balance equation can be written in this way. I have to account for some inputs of mass from the rainfall, some output of mass from the river discharge Q, and also some storage. So what I can write is that, let me start from the right-hand side. There is a mass of water getting into the catchment per unit time, PT. I have to subtract the mass of water flowing out of the catchment through the river per unit time. And the difference is precisely the change in time of W. And so I can write that the derivative of W with respect to time is equivalent to the difference PT minus QT. This is a mass balance equation, nothing more, which is applied to the control volume of the tank, meaning catchment plus underground. Okay. Now here I have what are the knowns here? The known variable is rainfall. Q is unknown. It's precisely my output, the variable that I want to describe. And W is instead another unknown, which is a kind of state variable. Okay, so I have two unknowns here. So I need a second equation. So what is the second equation? It must be a relationship between the two unknowns. Because of course I have to reach, if I have two unknowns, I have to reach a number of two equations. And these two equations, the second equation can be expressed as a relationship between the two unknowns. And the idea here is to use a linear relationship between storage and output. This is reasonable. I mean, the fact that I try to build a relationship between storage and river flow is reasonable, because the river flow is of course related to storage. So the higher the storage, the higher the river flow. And therefore, if I want to make it very simple, then the relationship is linear. And then I can write precisely the relationship in this way. WT is equal to the product of a constant K times QT. And this is my system of two equations. And look, this relationship here is linear. What does it mean, linear? So let me just put a box here. Linear. First of all, a linear relationship means that if you make a graph and a graph of WT and QT, this graph is expressed by a straight line. This means linear. But actually, in math terms, if you have a relationship, a linear relationship, and in this case, it's a linear relationship between Q and W. Now, so you have a relationship QT equal to FWT. What does it mean that it's linear? So here you have basically this relationship can be written in this way to write the conditions of linearity. So if let me refer to a general relationship F. It's linear if F AX is equal to A Fx. And it's linear if FA plus B is equal to FA plus FB. Okay, and so in basically, if I translate it in my example of the linear reservoir, my Q is a F of W. So it means that Q, which depends from W, so QAW is equal to AQW, and QW1 plus W2 is equal to QW1 plus QW2. This is the condition of linearity. And look, this condition, which is equivalent to this one, implies the superimposition principle, which means that you can get the river flow corresponding to the sum of two storages has the sum of the river flow due to storage 1 plus the river flow due to storage 2. This means linearity. Now let's go back to our system of equations here. I have two equations with two unknowns, which is now solvable. And the reason why I adopted a linear relationship for the second equation, for the lower one, is that I want to make it solvable through an analytical integration. Remember, these models were introduced when computers were not available. So people, when building mathematical models, had to rely on hand computation. Exciting time. Think of how would your life be like if you had to make any computation by hands. Would be completely different. But these people were able to solve the same problems that we solve today with more or less the same outcome. So they were able to make design. But of course, they had the brilliant idea of introducing simplifications, which to some extent we are still using, because now we don't have the constraint of the computer resources, which we have unlimited now. But we still have the constraint of reducing uncertainty. And the linear approximation, besides being less computational demanding, it's also less uncertain. Exciting time. But these people had to make any computation by hand. So this is why they wanted to make it linear. We will see that by adopting a linear relationship, we can integrate analytically this model. We can solve analytically this model. Okay, actually, the second equation, which is an empirical equation, we didn't use any physical motivation to motivate it. We just said we want a relationship between W and Q and make it linear. Now, the question is, from a physical point of view, what did I do by establishing a relationship between storage and river flow? What I did is simply working on conservation of energy, because if I establish a relationship between volume, mass, and so a relationship between a forcing and an outflow, a flow, this is conservation of energy. Because the more the energy, which is given by the volume, its potential energy, the more the flow, kinetic energy. It's an energy relationship. It's a conservation of energy. In fact, the relationship in hydraulics between storage in a tank and outflow from a bottom discharge is established by the Torricelli's law, which is based on conservation of energy. Torricelli's law is derived through conservation of energy. I'm not sure if you heard about Torricelli's law in your bachelor, but in any case, trust me, it's a conservation of energy law that allows us to compute the outflow from a tank. And actually, it's nonlinear. Torricelli's law, conservation of energy, in this specific case would be nonlinear. So what we adopted here is an approximation of a physical law of conservation of energy applied to the tank. And the approximation is just introduced to make it simpler. And now we are ready, once that we understood the physical motivation behind it. So it's a model based on conservation of mass and conservation of energy. And the conservation of energy is an approximation. Once that we know the physical motivation of it, we are ready to solve it. And then, with your permission, I integrate it, which is quite simple. You will see that we cannot get to let's say, to a true explicit solution of it. I mean, the analytical integration cannot be completed till obtaining an explicit solution for the river flow, but we will get very close to it. And so in order to make the integration, I need to open a new graphic sheet. And let me just, in the new sheet, let me expand it a little bit. And let me write again the system of equations. So it's, the system is, so dWt with respect to t is equal to Pt minus Qt. And the second is the linear relationship for the storage. Wt is equal to kQt. And this is my system. Now I can easily substitute the second equation into the first one. And then I obtain, so I can substitute here for Wt, I can substitute the product. Let me do like this. I put this into here, okay? And so what I obtain is simply K, which is a constant, so I can take it out of the derivative, dQt in dt is equal to Pt minus Qt. This proof, it's something I may ask you at the exam. It is quite simple, so I just would like to make you aware that it's maybe a typical question. Now, how can we integrate it? We have to multiply both sides of this equation times e to the power of t over k. And then I divide by k. So what I obtain is at the left-hand side, e to the power of t over k times dqt in dt. This is equal to, let me bring, sorry, control. Let me bring on everything on the left-hand side plus, oops, sorry, I moved it, plus e to the power of t over k qt in divided by k, because I divided everything by k, minus e to the power of t over k pt divided by k. And this is equal to 0. Now, let's focus on let me change the color, on the sum of these two terms. This can be written as the derivative with respect to time of what? Of the product. Oops, sorry. There is the span of the graphic blackboard, which is really troublesome because it is very easy to move the sheet instead of writing. So it's the derivative of the product e to the power of t over k times qt. Look, this is the derivative of a product. So the derivative of a product can be obtained by keeping the first factor as constant. So I keep constant this one, and then I take the derivative of the second one, which is, look above, look here, dqt divided by dt. Plus, now I take the derivative of the first, so the derivative of e to the power of t over k is precisely equal to the same factor, e to the power of t over k, divided by k times qt unchanged. So you can easily see that what is in the red circle above, it is the total derivative of the product within square parentheses below, okay? And then this is equal to, I put it, sorry, I changed the color to blue. I put it in the right-hand side, equal to e to the power of t over k pt divided by k. Now I can easily integrate. So by integrating between both sides, and let me integrate between a time 0, which is the starting time of my simulation, of the starting time of the model. Okay, so let's suppose that I want to apply the model from the beginning of a rainfall event, which I identified with the time 0. And then I extend the application of the model up to time t. And therefore, I can write basically integral between 0 and t of what? Of the left-hand side. I rewrite it, okay? I rewrite it in the derivative with respect to tau, because it's our variable of integration, which I identify with tau of what? Of e to the power of tau over k times q tau in the tau. Okay, this is nothing else than the integral of the left-hand side, and then again the integral of the right-hand side between 0 and t, e to the power of tau over k P tau divided by K in the tau. Very good. Now, at the left-hand side, it's an integral of a derivative. So what remains, it's just the argument of the derivative, which is e to the power of t over k q tau. And this is computed between 0 and t. Okay, the extreme of computations are 0 and t. And then at the right hand side, I have the same integral. I am just copying between 0 and t of e to the power of tau over k p tau divided by k in the tau. Good. Now, let's at the right hand side make this computation of the quantity between square parentheses, and so let me just go here in this part of our blackboard, and then I can write that I can write qt. I am computing the quantity in square parentheses for tau equal to t. So qt e to the power of t over k minus q0, because for time 0, you get that e to the power of 0, it's 1, so I just have q0, and this is equivalent to, I copy the same integral 0 and t e to the power of tau over k p of tau divided by k in the tau. Okay, now let's suppose that q0 is equal to 0. It means that when we start running the model, the river flow is 0. You can easily develop the result for q0 different from 0. It's not a problem. Just for simplicity of computation, let me assume that q0 is equal to 0. And then we can write simply that qt, I get an explicit expression for qt, which means that I have to divide both members, both sides, by e to the power of t over k, okay? And then, given that this is a constant, because e to the power of t over k, remember that t is fixed, it's the final time of the computation, so e to the power of t over k is a constant, so I can put it into the integral, and therefore I can directly write here integral between 0 and t of this thing 1 over k, which is the k here. It's this one, which is I bring it in front of the integral sign just for simplicity. And then I can write this multiplies e to the power of what? Of this minus t minus tau over k. Okay, and this is basically in the tau. That's it. And be careful, because I had to divide both sides by e to the power of t over k, which means that in the right-hand side, instead of getting only e to the power of tau over k, I have to divide it by e to the power of t over k, which means that I obtain, as a final result, e to the power of minus t minus tau over k. Okay, so that's it. This is the final result. And you see that there is still an integral there. And there is still an integral. Sorry, I am still missing something here, which is I am still missing precipitation, which is here, pt. So let me rewrite it, because otherwise it's not clear. Just 1 second. Okay, perfect. T minus tau over k, and then pt in the tau. Now it's completed. I was missing rainfall before. No? I forgot. You see that p tau is p tau. Sorry, p tau is in the line above. I forgot to copy it in the line in the final result. Okay, now there is still an integral there, which I cannot solve analytically unless I give a specification in mathematical terms of p tau, of precipitation. If I put there a relationship describing precipitation over time, and this relationship is analytically tractable, I may then get an analytical solution. Otherwise, if the relationship is not analytically tractable, then I have to solve the model through numerical integration. Numerical integration requires, some more computation. Now, let me give you an example of a relationship for rainfall that makes everything analytically tractable. And the simplest example that I can make is to take rainfall constant. So if rainfall is constant and I simply indicate it with the symbol P, I can resolve analytically it analytically. So let me write under the assumption Pt equal simply P, I can write Qt is equal to. Now let me bring out of the integration the constant quantities. So I can write P divided by K out of the integration, which multiply the integral between 0 and t of e to the power of minus t minus tau divided by k in the tau. And what remains into the integral can be easily, I can write again, I can simplify it more because there is still a constant quantity there. And the constant quantity is e to the power of minus t divided by k. So I can write it in this way to further simplify e to the power of minus t divided by k, which multiplies the integral between 0 and t of e to the power of tau over k in the tau. And then what remains inside the integral can be easily derived, easily integrated. And then the next step would be to make such integration. And then I can write Qt is equal to the ratio between P and K times E minus T divided by K, which multiplies the result of the integration. And the result of the integration is K E to the power of tau over K computed between 0 and t. Now let's make this computation of the quantity between square parentheses between the extremes of integration. So Qt is equal to P divided by K, E to the power of minus T divided by K, which multiplies what? K E to the power of T divided by K minus, and now we have to substitute 0 for tau, which means minus K. Okay, so everything can be written finally in this way. Qt is equal to P, which multiplies 1 minus E to the power of minus T over K. This is the final relationship, which is linear reservoir for constant rainfall. Good. Now, let me make you or show you better a sketch of the progress of river flow in this case. Just 1 second, because I wanna show you. I wanna show you the result in graphic form. So let me share again screen 1, and this is what you see. This is the progress of river flow against time with constant rainfall. Rainfall is the blue line and the red line is river flow with, remember, Q0 equal to 0. Okay, so you see that if rainfall continues over time, you have a river flow simulated by the linear reservoir that asymptotically converges to rainfall. Remember, it is the net rainfall volume per unit time. So you have the storage approaching a limiting value, which we don't know here. We could compute it by using the starting equations of the model. And what is most important, we have the river flow approaching a constant value, which is precisely given by rainfall. Now, let me go back to the PowerPoint presentation. So everything I did on the Blackboard is reported in my web pages. And now you see the computation reported in these slides and also reported in the pages. So you have everything computed. Let's go back. And now let's make a final discussion of this model. And I go to the web pages to make this final discussion. And let me see, I think it is here, the web page. And I just want to show you that on the web pages you see all the steps, all the math steps that I developed, everything is there, okay? And just a couple of final considerations, and then I close this lecture. So there are still some things that we need to discuss. And the first thing is the estimation of K. K is a parameter of the model. Like a parameter of the model for the rational formula was C. What is a parameter? A parameter is it's a component of the model equation, is a quantity in the model equations, which it's usually taken as constant, which we need to calibrate or optimize, which means that we need to define the value of the parameter which is plugged into the model equation to give flexibility. So if we tune the value of the parameter, we change the response of the model, and the model becomes able to adapt to different catchments. This is meant by flexibility. It's an essential element that allows you to adapt the model to your specific application. And so how can we calibrate this parameter? We can guess it. And there is a rule of thumb that says that K, which is, remember, it's a time. If you look at how K was defined, I go back. It was defined here through this relationship, which I show you on the screen. It was defined through this relationship. And if you make a dimensional analysis, you see that the unit of K is time. Okay, it's a time. So there is a rule of thumb which says that K is more or less equivalent to the time of concentration of the catchment. This is the rule of thumb. But actually what we do usually is to tune K through model calibration, which means that we found the best K values that reproduces at the best some observed values. So if we have some contemporary observed values of rainfall and river flow, then we can use the model to simulate the observed river flow. And by comparing simulation with observation, we get an assessment of model reliability, which in turn implies that we get an assessment of model uncertainty. And our aim, our target is to find the K value that minimizes uncertainty and in turn maximizes reliability. So this is how we estimate K, which is an essential element. The time K is an essential element of this model. And keep in mind that a high K values implies a larger storage into the catchment. And therefore, large values of K are appropriate for catchments with a large storage capacity. And also, in turn, a low K value means catchment with reduced storage capacity. So you go into a catchment, you look at the hill slope, and you see that they are impervious, which means that the storage capacity is reduced, and your conclusion is K should be low. And in graphical terms, if you look at the picture on the screen, a low K values implies a quick response, which means that the asymptotical convergence is fast. And while a catchment that responds slowly is a catchment with a large storage and therefore a large K. Okay, so I think it's we need to stop here, and I wonder whether you have any question. Let me share the screen and let me look at the chat. Okay, I don't see any question. And again, I have another meeting starting soon. So I would propose that if you have any doubt, question pending, let's make a recap of what we did on Thursday. We meet again on Thursday, and then I will ask you at that time if you have any question. Very good. So let me stop the recording.